All right. Okay, guys. I want to finish up what we have discussed the last time. We are talking about a very important event happening inside the computer, right? Exception and interrupt, right? So take a look at this PowerPoint. This is very important PowerPoint, and also I drew, uh, the execution flow when exception happens inside the computer. Um, Okay, so we are assuming, right? So you are assuming you are executing some main program, CPU is executing main program, and exception is generated in the middle. And last time, we added what? The example code. We added undefined the instruction. These four apps, this machine code, this is the machine code actually. So, this is not understood by CPU. So CPU is trying to execute this code and exception is generated. Undefined instruction exception. In Cortex-M processor, this one is called hard fault exception. Okay, there are many, reasons why hard fault exception occurs, and one of them is undefined instruction, right? So this is the execution flow when exception happens or interrupt happens, right? Every CPU is implementing interrupt vector table or exception vector table, right? And the format is again, different depending on CPU vendors, right? x86 has its own vector table format. RISC-V has its own vector table format, right? And ARM has its own vector table format. Even inside ARM, we are talking about Cortex-M0, ARM version 6, M architecture. But in version 7 architecture, this vector table format is also different. And version 8, vector table format is also different, right? Anyway, the good news is, every CPU, every architecture is specifying this vector table. So you have to go through this vector table to execute the code you need to execute when exception happens, right? Okay, so that is an important thing. And last time we discussed, hardware operation happening during that transition. This is very important. So why is it important? Because when exception happens, what should be done is you need to preserve the last state of the program. And when you return back from exception handler, you have to resume from the last state. So the point is somehow you have to back up this state, right? And important thing is hardware is doing some backup operation for yourself, for you, and then the rest should be taken care by software, right? So to figure out what you have to backup, push, and here pop in software, you have to figure you need to know what hardware is doing uh, when exception happens, when interrupt happens, and these are detailed operation. Cortex-M0 CPU is doing when exception happens. So first one is this one, CPU context, not everything, right? CPU context backup. How many? 1, 2, 3, 4. R02, R3 is 4 registers, and R12 link register. Link register will be saved in memory because if, check out this bullet, because the link register will be updated with one of these special code. Okay, this is very important. This one R14 will be updated with one of these special code. Okay, and then when you return, so let me explain. When you return, you have to use branch and exchange and LR register. And according to the table, in our example code, link register will be updated with that information. 7 apps and 9, right? And the value, uh, uh, so one of these three values, right? So what does that mean? So depending on the value, the return behavior is a little bit different, right? So these two first. So we are talking about this, F9. So you assume that you have 7 apps and 9 stored in link register, and you execute this code. And then this is not normal, the return code. It is exception return, exception return code, because link register contains this special code, right? And the behavior is CPU behavior, hardware behavior. Hardware, during this transition, hardware is doing first opposite operation of this. This is a push operation, right? So R02, this 8 data, is 4, 5, 6, 7, 8. These 8 words are pushed, are saved in memory, and this one is opposite operation from the stack, from the memory. You are updating these 8. You are updating these 8 registers with the memory content you saved during this transition, right? And then second bullet. Second bullet is important. Depending on this special code, these two, you are returning, and you are using main stack pointer. So there are two stack pointers: process stack pointer, main stack pointer. So if you have a 9, and if you have 1, 7% 1 in link register and execute this code, then when you return back, CPU will be using this main stack pointer. Okay, and link register has this special code 1. Then you are returning back to handler mode. Okay? So handler mode. And if you have a 9 in link register, then you are returning to thread mode. Cortex-M0 is providing only 2 different operating modes. Check out this PowerPoint, right? We have, where is that? These the details of this one. Okay, thread mode and handler mode. Our Cortex-M0 is providing only 2 different operating mode. When you turn on Z board, when you turn on zero board, when you reset zero board, then CPU goes to thread mode by default. Thread mode. Okay. Then exception happens. Uh, exception processing is exception processing is done always in handler mode. So handler mode, right? So reset. Right after reset, you are in thread mode, right? Exception happens, then you go to handler mode, right? So here, so in the main, you can switch it to handler mode by using this control register. Control register and first bit, the first bit. Okay, confusing. Control register, handler mode, thread mode. Too many registers. Let me back. And, okay, this is not the one. Handler mode, thread. Okay, you can change stack pointer, current stack. Stack pointer. Okay, stack pointer you are using. Mm. So okay, thread handler mode. Probably you cannot change operating mode. So you can only select. You can only select. Okay, I'll figure it out later on. Okay, don't worry too much. Okay. So anyway, so after reset, you are in thread mode. So you are executing your program, and then exception happens. You go to handler mode, right? So let's go back to here. Okay, go back to here. Okay. So depending on the special code, if you have a 1 in the link register and execute this code, then you go back to handler mode. And when you return back, you are using main stack pointer, right? And this one, you go to thread mode. Okay, thread mode, and then you are using main stack pointer. Okay, if you have a T, then you return to thread mode, and you use a process stack pointer. Process stack pointer. So the point is, which stack pointer you are going to use when you return back, and which operating mode you are going to be in when you return, right? So that will be differentiated depending on this special code. Okay. So in our example, a thread mode, you execute your main code and exception happens, undefined exception. Then a link register will contain this special value F9. And we have been using main stack pointer here, right? We have been using main stack pointer. While using main stack pointer, exception got generated. Exception generated. So when you return back, you have to use the main stack pointer, right? So that is this one, F9. When you return back, you go to thread mode, and you are using main stack pointer, right? So that is the one. Okay. Uh, then here, so let me continue. So second bullet, during this transition, CPU will switch it to handler mode, right? Handler mode. You are exception. You are going to do exception handling. So intuitive, right? Name. You go to handler mode, right? And then IPSR interrupt processor register, status register interrupt will contain exception number. And there is a unique exception number depending on event type, right? So where is that? Refresh your memory. So this is exception number. So in case of hard faulty exception, right? Undefined instruction is one of hard faulty exception. So 3, this number will be recorded in IPSR number 3, right? That is hard faulty exception. And program counter will be updated, right? So here program counter will be updated with that content. So that vector table. So we have 48 entries in our Cortex-M0. Okay, and then number 3 is hard faulty exception. Hard faulty exception. Okay, so CPU will read this content and update program counter. Okay, then what happens? Program. So this content is what? Content is this one. Memory location of the first instruction in this hard fault handler, right? So read that that content and update program counter. CPU is going to do that operation. So let me show you a demo now. It is not efficient to give online lecture. So there's no one here. So it looks like I'm talking to talking to no one, right? So, okay, so let me execute this one. And then this assembly code. Assembly code is generating undefined exception. Let me compile this. Then Alt F5, okay. F5. Okay, let me run instruction by instruction, sentence by sentence, F11, 11. Okay, we are calling assembly code, and this assembly code is just uh, initializing R02, R7, and R8 to R with these data. Okay, because we want to check out that we want to do this, right? The state should be preserved, right? So exception happens, we want to dump out memory contents to figure out these these registers. So R02, R3 according to that PowerPoint, right? R02, R3, R12, those registers, those data are pushed onto the stack. Right? We want to check that out. Okay, so let me execute instruction by instruction. Now these registers are filled with the data. Okay, now so now check out check out main stack pointer. Main stack pointer. uh, Main stack pointer. Okay. Main stack pointer value 230s 2458 2458. And let me draw memory, right? So we have memory. Let's say starting from 0 is incrementing like this, and this location 230s 2458. Okay, so that is the main stack pointer. MSP contains this information, and then remember when we discuss data processing instruction, sorry, memory access instruction. Memory access instruction, multiple data transfer instruction, LDM, STM. Okay, LDM, STM. We discussed in detail about multiple data transfer instructions, right? Remember this row, high, high, low, low rule, right? This one. So R0 register will be stored in low memory location, and this one last data, PSR, will be stored in high memory location. And all we are talking about full descending stack. There is a default stack, right? Full descending, right? I'll show you full descending stack. That means the location stack pointer is pointing full descending. The location stack pointer is pointing is already full, occupied, right? So to push data, first data, so stack pointer should be decremented by 4 first, right? Stack pointer should be decremented first. Okay. Then according to high, high, low, low rule, right? High, low, low. And then the first data you have to store is PSR. Okay. And then what? A return address. Return address RA will be stored. And then link register R14. Okay, and R12, then R3, 2, 1, 0. This is 8. 1, 2, 3, 4, 5, 6, 7, 8 data. So stack pointer will be pointing that location. So 8 data. 8 data will be stored, right? So 1, 2, 3, 4, 5, 6, 7, 8. Then the final location, the stack pointer is pointing, 8, right? 8. So the number 200024, you have to do subtraction. Extraction 20, 20. Okay, do subtraction, right? So 3, 8. Stack pointer will be will contain 3, 2, 4, 3, 8 at at the beginning of uh this exception handler. Okay, so let me show you that behavior. So okay, so memory, right? We have to check out memory. So let me show you 2, 3 zeros here. Oh, so okay, this number. Okay, this one is okay, pretty good. 2, 4, 2, 4, 2, 4, 5, 0, about 5, 0. And I want to see 16, 16, data, 16 byte, 16 byte in one row. Okay, that would be pretty. So this one, okay. So 5, 8. So 5, 0, 5, 4, and 5, 8. Okay, so it is incrementing also, right? So it is incrementing like this, incrementing. So decrementing, right? Full descending. So these data will be updated. Okay, let me press F11. Okay, first 11. So see, here first a stack pointer. Stack pointer 3, 4, 2, 4, 3, 8. Right, 2, 4, 3, 8. This information, okay, because we push it 8 words. 8 words, right? 8 multiplied by 4, 32 bytes, right? 32, 20. Okay, then check out this stack, the memory content, 5, 4, starting from 5, 4, right? So this is the 5, 0, and this one 5, 4. Okay, so 138. So this one is PSR. PSR. So so before and after, right? Before information, I don't know what was PSR. PSR is what? Uh, interrupt PSR, execution PSR, and this one, right? This PSR, right? So these three combined, right? So I think zero, only T bit is one. So 0, 1. Zero, how to read 0, 1? How to read 0, 1? Then next 0, 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0. So 1. 1 means this one, T-bit execution PSR. And then this one, 4, 0, 0, 0, 0. Probably NGCB were 0 before exception got generated, I think. Okay, anyway, this is the one. And then this one is what? Return address. So how to interpret 138? 138. Check out check out LSS. Output file, LSS, LSS. Oh, not okay, LSS. Cannot LSS, please. It cannot be. Cannot see. So why is that? LSS. Virtual file load exception. I want to see. I want to show you the the disassembled code. So but why? Why is that? Okay, let me show you first. Remember this, right? So return address was what? 0x 138. 138. I think 138. Okay, then okay. Then check out this one. LR, link register, right? Link register should be updated with one of three special code, right? So here, link register got updated with this number, right? This is special code, F9, okay? And then this one is also important information, IPSR, interrupt PSR. So exception number, right? You're talking about hard faulty exception, and number three is assigned for hard faulty exception. So check out IPSR 3. Okay. So yeah. So this one now we are turning on, right? This is not doing anything serious, right? So we are turning on LED. So we can just execute this code F11. We are returning back to the the main code, but we are returning back to this place. We are returning back to this place. That is why we are executing hard fault exception handler again. Because exception got generated again, right? So why it is returning back to this place? Check out our point. I think slide number 34, 35. Okay, check out. This one is also from architecture specification. So exception entry behavior. When exception happens, so hardware is going to do this operation, right? So memory location, right? R0, memory location, R1, R2, right? This is the one, right? And then return address is saved, right? But the return address is different depending on exception type, okay? Exception type, right? And then next page, look at this. Exception type is hard faulty exception. And then if it is a synchronous exception, then return address is going to be this instructions address. This instructions address. It is, undefined instruction exception is synchronous event. So CPU knows, right? So this place. But if you think about hardware interrupt, there is asynchronous event, right? CPU does not know. CPU has no idea, right? When that event would happen, right? It is asynchronous to CPU clock, right? CPU. But this one is a synchronous event. So returning back to this instruction. So the return address. So return occasion is determined by actually, the architecture, CPU architect. and that is also described in the architecture specification, right? You have to you can figure that out, the return location, depending on exception, type, right? So that code is doing that operation. Okay, so last behavior. When you are returning back, again you have to execute that instruction BL and LR. LR will contain one of these three special code, and in our demo code we have this code stored in link register. Okay, and then so second bullet, right? The first bullet is the very obvious operation, right? So in opposite operation of that stack push, stack pop from the stack, right? And the second, the mode, operating mode. So when you return back, operating mode, CPU operating mode, and stack pointer, which stack pointer you are going to use when you return back, that is determined based on the special code. Right? So one, then you are returning back to handler mode, and main stack pointer will be used. And state restore, this state restore is based on also main stack pointer. 9, then you are returning back to thread mode. Okay, thread mode, and then state will be restored. This is state restore, first bullet. State restore will be happening from main stack pointer. Also, when you return, you'll be using main stack pointer. So T, you can figure it out, process stack pointer. State will be restored from process stack pointer. Right? Okay, there is exception. Let me finish this one. Okay, then compile it again. F7. Okay, let me try to open LSS. Why? LSS. Something is wrong. I don't know. I'm trying to show you this one, 138. At 138 location, what is in 138 location, right? That is what I wanted to show you. What do I mean? I'm trying to show you demo, then something very strange is happening every time. I don't know. Last time in the class, there was no problem, right? LSS opened without any problem, right? Okay. Solution progress. Compare it again. Log file. Yeah, no problem, right? I don't know. So let's go back to 138. 138, right? So 138 location, return address. 138 is this undefined instructions location, right? So in this case, we are returning back to that instructions location. Okay. Okay. Now one last demo. So in the example code, assembly code. Let me show you this one. Comment out this. And this one is also generating a hard fault exception. Memory read instruction, right? And you are reading from this location. This is not a 4-byte aligned location. The 3, right? Odd number. So it is not 4-byte aligned location. So if you are attempting to execute that load instruction, then hard fault exception will be generated. So go back to that what kind of event belong to here, right? So, hard faulty exception, right? These all hard faulty exception. So this one, undefined instruction is one of hard faulty exception, and unaligned load or store, that is also hard faulty exception, right? So let me execute that, code 7. Okay, Alt F5. Let me set breakpoint. Breakpoint at here. Then press F. F what? 5. Continue 5. Okay, stops here. Okay. Breakpoint. Remove breakpoint. Okay. F11. Okay. R0 contains. Again, now before, right? F11 one more time. So this one, and we are about to execute LDR instruction on aligned memory read instruction. Okay, then same, right? You can do this, right? Stack pointer is this value, and link register before exception generated this value, but this link register should be updated to memory, right? Because link register will be updated with one of special code, right? So let me run by pressing F11. So hard fault exception got generated. Check out this value. So link register contains this special code F9. Then interrupt PSR also 3. Right? So then let me execute F11. 11 returning back to that place. So CPU is trying to execute that code, right? Again. So, according to architecture specification, unaligned memory access, you are returning back to that place again. Right? So F11, exception generated again, right? So, oops, F10, 11, okay, okay. So exception will be generated continuously, right? So that is another exception case. Okay, then stop this. And if you check out LSS file, so check out this LSS, right? During this transition, hard fault exception handler is in C code, and hardware is backing up these registers, right? These registers are 12, are 14, and these things, right? So uh, probably you are curious, right? You haven't done. We are not doing assembly programming. We are so this demo code handler is in C. Handler is a C code, right? So check out disassembled version of that hard fault handler. What kind of registers are being are being used to run this code? We are talking about this state change, state preserving state, right? So output file LSS again, hard fault handler. Please again. I don't know what is happening. LSS. Okay. So hard fault. Okay, here. Check out this. That is the disassembled version of hard fault handler. Check out this destination register, LDR instruction, R3, R0, R1, R0, R1, R3. So those registers, right? R0 to R3, those registers are being updated inside hard fault handler. Right? Probably because this code is very simple. So exception handler is super simple, right? So I edit. So let me show you this. I edit, but this LiDAR, code. LiDAR code is pretty complicated, right? So let me open up. So where is main LiDAR? LiDAR code here. So main, pretty, this main LiDAR, pretty complicated. So you have to use, probably all of general purpose register. I don't know how compiler will behave, but let me compile this. If we compile this and check out RSS output, RSS hard fault handler, same thing, R2, 3, 0, R1, R0, those registers, or saved in memory by hardware, right? And then you are calling this one, main writer. Check out main, right? Okay, this code. Look at this. Compiler is pushing 4, 5, 6, 7, and link register. Amazing, right? So not, these four, not first four. 0, 1, 2, 3 are not pushed. 4, 5, 6, 7. And link register got pushed. Because inside the main writer, you are updating those registers. Right? Probably compiler is aware of that exception behavior of hardware. Exception, behavior. What is happening during this transition? Right? Okay, that is about. Probably you can dig into the detail, right? Why, how compiler knows, right? So how compiler pushes only those registers. Okay. Okay. So we have done now exception handling, right? So from Monday, right? From Monday, we are going to talk about hardware interrupt, hardware interrupt, right? Interrupt from I/O devices, interrupt from sensor, right? Those stuff. Okay, I'll see you on Monday. Bye.